Hey, good evening, everyone. So today we'll be doing section 1110 on Taylor series and Maclaurin series, but the Maclaurin series is a Taylor series where that A value right there is just 0. That means centered at 0. So when you hear this term Maclaurin series, I know you'll know just to make the A a 0. So with these Taylor series, I can put it up right here. We're talking about some function of x, where we can actually let that function be equivalent to some power series, where this is the nth derivative evaluated at some, actually you'll see with the, let me make sure it's an A. Nth derivative evaluated at A. I apologize. So the nth derivative evaluated at A times x minus a, all raised to the n, divided by n factorial. So this is a Taylor series. We represent functions this way. And there's really 3 key portions that we'll be dealing with when we work these problems. We'll be thinking of. That's the nth derivative evaluated at a. So if you want to put that in your notes, like, what does that mean? You may have never seen this notation before. That's meaning the nth derivative. Like when we plug in a 1, that'll be the first derivative. When we plug in a 2, that'll be the second derivative. But then we'll evaluate it at a, whatever the a is, phase of 1 or phase of 0. In terms of the Maclaurin series. That's just n factorial, we know about that, and this will just be x minus a. Yeah. So the problem we're going to start with, we're going to find a Taylor series for, here's the function. Find a Taylor series. For the function f of x equal to e to the 4x. Where it's centered at the value of 2. But I'll just put like the textbook, that's how they wrote it. I want to write it like you do it in the textbook. They provide the function, they can give it a value. That means it's centered at 2. So I can put that close. Centered at a. That a is just the next value. So we're going to find a Taylor series for function e to the 4x, where a equals 2. At the end, we're also going to find the associated radius of convergence. So we'll start with this. And then letter B. Let's find the associated radius of convergence okay. So 3 things will be going on. Nth derivative evaluated at the a value, x minus a to the n factorial when we set this up. So I like to present what will this look like without that. In the end, this is what will happen. What's the a value in this problem? 2. So we're going to have some number times x minus 2, plug in a 0 over 0 factorial. Plus some number, x minus 2 raised to the 1 over 1 factorial. Plus some number, x minus 2 squared over 2 factorial, plus dot, dot, dot. It's going to continue. But each problem we do is going to have this type of setup. This will be easy. This and this, right? And they give you another function. We'll do the same thing. X minus 2, x minus 2, x minus 2, just 0, 1, 2. We're plugging in the 0 and the 1 and the 2. These boxes, though, are related to this right here. And that's the nth derivative of that function. So it helps. That's the only hard part. So it might help to just set up a table, and we'll evaluate all the derivatives. Okay, the first derivative, the second derivative, and the third derivative, and then we can plug them back in here. We'll evaluate them all at the value of a equal to 2. So let's just go off to the side here. We can build a little table here with the column. And let's make a column for the nth derivative of x. So we got to figure out the nth derivative of x. And then we'll make a third column, and let's figure out the nth derivative evaluated at the a value. So I can put an a here, but what's the a value? It's probably 2. All you'll do in the Maclaurin series is you evaluate it at zeros. All the nth derivatives. All right, so the first number we have to start with, don't start at 1, make sure you start with 0. See how the series starts with 0? Taylor series, that's n equals 0, n equals 1, n equals 2, etc. All right. So let's do this. All right, what's the function? You go, what, the 0 derivative? They're talking about the original function. So don't let this confuse you. When it's 0, everyone put down the original f of x, which is what? E to the 4x. Okay. Now, if you plug a 2 in there, what do you get? E to the a. And then we'll continue. Right at 1, 2, 3. Students always ask me, how far do I go? I would go out at least like 3 or 4 terms until you see the pattern where you can actually write that Taylor series in sigma notation. And that's what we're going to do. We're going to write it in sigma notation. If you want, we can even go to a 4th. I think we got all this. All right. Derivatives. What's the derivative of e to the 4x? Is it e to the 4x? You're good. 4 e to the 4x. So what would this value be? That means just plug a 2 in there. 4 e to the 8. Hey, as you're writing, if this was a Maclaurin series, you would have plugged in a 0. What's 4 times e to the 0? 4. I mean, just to compare. If you see that word Maclaurin series up here, what's going to happen when we do those? We evaluate everything at 0. These are zeros. X minus zeros. All right, what's the derivative of 4e to 4x? 4 times 4e to the 4x. I heard it 16 times e to the 4x. This is how I'm going to write it, though. I'm going to write it as 4 squared e to the 4x. Of course, you could write 16 e to the 4x. I'm going to write 4 squared e to the 4x because eventually you and I are going to want to set up a sigma notation. I think writing it this way will help us. Will help us write it. All right, what's this? What do you get here? You get 4 squared times e to the 8, right? 4 squared times e to the 8. If you want to write 4 squared e to the 8, you can do that too. Now, even though I did it here, if you're like, no, I'm going to write it as 4 squared e to the 8. That's totally fine. Let me make sure it doesn't say e8. E raised to the 8. And let's do the n equals 3. What do you get? What's 4 times 4 squared? 4 cubed. 4 cubed. Usually you can sense a pattern out of this. What's this become? 4 cubed. Okay, so far? I think we've gone far enough where we can actually present the solution, the Taylor series, in sigma notation. But, see those boxes I left there? Now I get to plug the numbers. This goes there. This goes there. See how that's for 1? This number right here goes right there. Oh, I ran out of room, but I would have put that next one in the next one. This would go to the next one. All right, let's put it in there. What's right here? E to the 8. This is, I'll take the box off, 4 e to the 8. This is 16 e to the 8. Or, even if you want to write it the way I was talking about, because I know you know 4 squared is 16, I'm like, well, I'm going to write it like this. 4 squared e to the 8. So that you and I can come up with the solution to letter A. So we're going to write this in sigma notation. That's called a Taylor polynomial. Would you put that in your notes? The last section we do, we'll do that. after section 1110, they call them Taylor polynomials. Do you notice that's a polynomial? So this is actually pretty cool what we're doing. We're rewriting the function e to the 4x as a polynomial. But it's heading towards what? Infinity. We're getting all these terms. Well, we'll write the first root term so we can get a sense of what will this form will be, how it can represent it. So in sigma notation, Owen, can you help me rewrite this? I'm going to have to write all this in terms of a sigma notation. So here, n still equals 0 goes to infinity, right? Looks like we got an x minus 2 to the n. What's in the denominator?
N factorial.
N factorial, but this is what I need you to study. You're going to look at what you got here, what you presented up there, and you're going to rewrite what is being represented for each nth term. Do you know, Isaac?
4 to the n, e to the 8.
Brilliant. He looked at this, he goes, what's happening here is just going to be 4 to the n, e to the 8. And that's why I wrote it like this, because see the 2 and the 2 and the 2? Isn't that 4 to the 1, 1 and 1? Where's the 4 though? That'd be 4 to what power? I mean 4 times 4 to the 0 power, which is 1. So does everyone see? He's saying right here, we can represent that as 4 to the n, e to the 8. All right, I'll put it right here. 4 to the n power times e to the 8, unless you want to write e to the 8. There it is. You can check it. I mean, you can go back and check it. Like, let me see. If I plug in a 0, do I get this? If I plug in a 1, do I get this? And please note, this is really a what? It's a polynomial. In section 1111, they go, find the Taylor polynomial. You're like, it's the same thing. We'll just write it as a polynomial. What we're doing right now is we're writing it as a series. We're going to write it as a series. So find a Taylor series, okay, we'll write the solution as a series. But this is how we write it. We won't leave it in that format. We'll simplify it and say this is your Taylor series right here. Make sure everyone sees this. So that's what I mean by in sigma notation, how to write the final answer. And you might prefer to write your derivatives in this way. Rather than 16 and 64 as 4 squared, 4 cubed, 4, so you can sense that pattern. So it makes this easier. Like Isaac was able to just say what? 4 to the n. But the e to the 8 was constant, so we had to just put an e to the 8. Anyone okay with that? Hey, are we done? Well, this is part B. Super duper, and this is really cool stuff. We're saying that this function right here, that we've dealt with before, this e to the x function, is equivalent to this. Yeah, but for what x values? You know, is it only like from -1 to 1, or what's the radius of convergence? So that's what we're going to talk about. That's important to the programmers in here. When I write a program, can I use all x values, and this works, to represent a function e to the 4x, or only certain x values? So we're now going to find the associated radius of convergence. So this is what we did yesterday. We just get more practice. So this is the 11.8 stuff. What test do we always use? Let's go to an R. You're good. We'll do the ratio test. We're going to find the associated radius of convergence. See what's happening with this one. All right, so let's do the ratio test. Limit n approaches infinity. We got to do the absolute value, right? Now, what am I doing it on? In this right here. So when you're taking your answer in letter A, that's the solution. We're going to find the associated radius of convergence. So when 4 to the n plus 1, right? Did I write that correctly? No. These are the little things that can just, I mean, you go, I would have aced that test. Little things like this. Did I do that right? It's what? 4 to the little tiny n plus 1. Now, there's an e to the 8 there. Do I do e to the 8 plus 1? No, you're good. That's a constant. So just put e to the 8. It just stays. All right, keep going. What's this keep going? Oh, x minus 2, n minus 1, n plus 1, excuse me. Dave, feel free to do 2 steps at once. Others probably agree with you. And what's this all over? N plus 1. Now, do you recall yesterday? That's the a sub n plus 1. Now we put a big fraction bar and we do a sub n underneath. Which means we multiply the reciprocal, so I'm going to go right to that. Stretch out these absolute value bars. I've got enough room right here. And what goes up here? And factorial. Then all that goes below. 4 to the n, e to the 8, x minus 2 to the n. And there's something I forgot to write. I bet you'll find it. Everyone's good. Yes, you're good. It's like, what am I doing? I'm evaluating this. We're finding that x. And we're going to say this limit less than 1. So I want to highlight what we're doing right now. We're trying to find the radius of convergence for that x right there. You don't have to highlight the minus 2, but it's all about the x. All right. Now, can you help me simplify this? I know you can. That's 4 to the n times what? All right, 4 to the n times 4. 4 to the n times 4. That's just an e to the 8. That's x minus 2 to the n times x minus 2. N plus 1 factorial. We'll deal with that in a second. Then what do I have in the denominator? I've got a 4 to the n, e to the 8, and an x minus 2 to the n. Many people usually like to do 2 steps at once. Some of you might have gone right to this in your first step. That's okay. What cancels? Okay, the e to the 8 is out. X minus 2 to the n, you're out. What else? The 4 to the n. Now I want to be careful when I'm scratching out, I don't scratch out something that I got to keep, like that 4 stage, right? So keep that 4, make sure I don't let it disappear. That 4 is still there. I've got the x minus 2. Now let's talk about this off to the side. How do you simplify this? Some of you just do it in your head. That's 1 over n plus 1. Right, everyone? Again, I want to show you why, but why do you just go, that's 1 over n plus 1. This is because the top would be what? N times n minus 1 times dot, 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 dot. What's the bottom? That's an n plus 1. What's 1 less than that? N, and another n minus 1, and everything cancels except for the 1 over the n plus 1. So that's what's, I'm going to replace this right here. Let me just put it like a bracket. All that is going to get simplified to 1 over n plus 1. And I'm going to put this in front of the limit so it highlights it. So I now have this. X minus 2, limit, and approaches infinity. And I got to get that 4 in there, right? Anything else? What's in the bottom? S plus 1, and we're finding this limit, and it's less than 1, right, everyone? Well, I'll just check it over, everyone. The n factorial over n plus 1 factorial is 1 over n plus 1, true? I didn't forget about that 4, there it is. I'm going to pull this out here, though. So it's not my way, you can help me get that limit. What is that limit? Okay, this happened once yesterday. When that's a 0, it's a very interesting answer for the radius of convergence. Do you recall? It's not, does not exist. It's the complete opposite. I heard it. Here's your radius of convergence. Infinity. That means the interval is negative infinity to positive infinity. So here's the interval. The interval would be all real numbers. How cool is that? This power series right here, this Taylor series, is equivalent to this. As long as you set it towards positive infinity, you can write a program. Program this into a calculator, into a computer. And you can now figure out values of e to the 4th, e to the 8th, e to etc. I mean, isn't that cool? Because it's just some irrational number to write a program to do that. So I'll think of it as a polynomial. Pretty neat stuff. Hey, we're going to go that. Hey, we're going to do a Maclaurin series eventually. I do want to point out, I want to get that table. This is just actually a table out of the book. It's table 1. You'll see it in this section. but they're important Maclaurin series. Well, this wasn't helpful here because this wasn't a Maclaurin series, was it? The Maclaurin series is when A equals 0, this was A equal to what? 2. So we really had to go through the math to really see what was happening right here. But some of you might want to get familiar with these because look on this sheet right now. Do you see an e to the x anywhere? Was the answer somewhat similar to this? Like look at what they have here. What does it say for the function e to the x? What's it equivalent to? It says the summation n equals 0 to infinity of x to the n over n factorial. Doesn't it look like that? So what I mean is knowing that can be helpful in like what you kind of expect to get right here. True? And here's another big thing that helps. What's the radius of convergence on this sheet for e to the x? What was it? Someone see it? It's infinity. And look what we got. We got infinity. So that really kind of helps if you're just familiar with them. No, I'm not forcing you to say, hey, memorize all these. You definitely have to know the first one. So make a star by that one, because that was the one from yesterday. The 1 over 1 minus x, what's that equal to? Just the summation of x to the n. That's from the geometric series, right? We got that, but the rest of these, I'm saying, do I have to memorize these? I'm always saying it. I think it could be beneficial. A lot of my colleagues agree with me. If you know these, or at least like the e to the x, the sine of x, and the cosine of x, then when you have to deal with it, you're going to get a solution that should be somewhat similar if it's a Taylor series. All right, let's do another one. Great job with that. This problem was like number 17 from the practice problems that I gave you. It was like number 17. I want to do number 18 from the book. So, you know, the even answers aren't in the back, so I'm going to do exactly number 18. I can erase this. I can erase that. And that. I'll erase my table. Erase all this. Let's do another one. Now it's all fun. Let's look at different functions. This is exponential. Let's look at a trig function. Let's go look at a trig function. Okay. This is number 18 from the book. What's it say? The function. Sine of x. The function sine of x. The a value centered at pi over 2. So it's centered at the value pi over 2. Okay. Taylor series function of x is sine of x at a equal to pi over 2. But I can leave my table here because we're just going to get another table. Hey, when it comes to sine and cosine, I actually think it helps. You go, can I just go out the 3 terms? Actually, this was 4 terms. Didn't we just find 4 terms? But you might go out a little bit further. Where are we evaluating all these at? At pi over 2. So I'm going to put a pi over 2. The best of Maclaurin series, where you evaluate them at 0. You get things like e to the 0 power, 1. But you got to deal with sine of 0 and cosine 0, which can be kind of weird. All right, I'm going to set this thing up. I always do this first. You don't have to. Box. Then I'm going to get x minus 0 to the 0 power all over 0 factorial, right? Plus box 1 factorial x minus 1 to the first power. Plus box x minus 2 raised to a 2 over 2 factorial plus box x minus, oops, not 0, 1, 2, I apologize, what was the center? Did you get that right? The center was what? Pi over 2, so I'm going to put pi over 2's and all these x minus pi over 2, x minus pi over 2, x minus pi over 2, to the third, all over 3 factorial. And down here at the end, I can just put plus dot dot dot, because this will just continue. The reason I write it like this, I want you to notice that every time you find a Taylor series, your answer will look the same in terms of the setup, right? This is like the last problem. It's all about those boxes, though, that come from here. the boxes, we're going to find this number and put it there. We're going to find this number and put it there. We're going to find this value, put it right there. We're going to find this number and put it right there, right? The derivatives. But other than that, you're like, oh, don't let this thing confuse you. You're like, everything looks like this. And they're polynomials. It's a polynomial. All right, let's start out. What goes in the zero part? Just the sign of x, right? All right, put that there, sign of x. The original. What is the sign of pi over 2, though? 1. Good job. Hey, what if this was centered at 0? I would have been starting with a what? 0. You got it. I remember before. 0. All right, what's the derivative sign?
Cosine.
Cosine of x. Hey, maybe I should write this down to help me out. S, C, S, C, S. Where are the negatives? Here? And I'm differentiating, so I'm going that way, right? Just to help me out. Okay, what's the cosine of pi over 2?
0.
This is interesting, comparing this problem to the last problem. Do you agree? This was a lot more busier last time. These are coming out kind of neat. The 2. What's the cosine? Negative sine of x. You bet. I could have done sine of 2x. We would have done chain rule. We get it. We get it. But I thought, let's do number 18. All right, now we need negative sine of pi over 2.
Negative 1.
Negative 1. How about the derivative of negative sine of x?
Negative cosine.
Negative cosine of x. What's negative cosine of pi over 2?
0.
0. What's the negative cosine of x? I think we've done full circle.
Sine.
So that's why you'll notice for a trig function I go out a little bit further. I want to go that full circle to see, all right, now it's going to just repeat. Right? This is going to be like this. And sine of pi over 2 is just a 1. So that's why I went out that far. I wanted to see where this started to just catch up and start doing the same pattern. You know, I can do a 5, 6, 7, 8, and just keep doing this. If you want to keep writing it, if you want to continue your column, go ahead. Keep going. You can see it would just keep doing the same thing. All right, let's put these numbers in here. Where's that count? Here, there. 0. That's interesting. We're getting zeros. So in that 0 there, do you agree it's going to wipe this out? It's going to wipe it out clean. Okay. That's up. Negative 1. That's up. Okay. So this time, got these arrows out. Good job, everyone. Don't want to be messy here. This time, it's nice and neat. Get this out of the way. We're going to write our solution in sigma notation, right? Before we do that, maybe different from the last problem, can we rewrite this? If these are zeros, they are what? They're gone, aren't they? This one and this one. So what do I have here? I have a 1 times x minus pi over 2 to the 0 power 0 factorial. Oh, what is 0 factorial? It is not 0. 1. So I make a note of that. That's really important. We need to know that. 0 factorial, by definition, is a 1. You can check it on your calculator. I'm writing it like this so you can help me figure out the pattern. That's why I'm not putting a 1 there. So 0 factorial. This went away. What's still there?
Negative 1.
Plus negative 1, but I got to be careful. What's the power now?
2.
2 over 2 factorial. Plus here, just do a dot, dot, dot. And you and I are going to figure out the formula for this Taylor series, and we're going to put it in sigma notation. This will be in sigma notation. That's what they call it, sigma notation, where we put that funny looking sigma symbol like this. Start at 0 and go to infinity, right? But I'm being honest, you go, wow, if I knew the McLaurin series on that sheet, that might help me do this. I don't know, though. I don't know. All right, we got to figure this one out. The hardest part, we got to talk about this. Hardest part. What makes something go by 2s here? And what I mean is, 0, 2, we know the next power is going to be what? 4. We all see the pattern, don't you? I mean, if you wanted to, you could have gone further, but we see it's doing every even power. 0, then 2, then 4, then 6, then 8. And you can bet, you can say 0 is even. 0, 2, 4, 6, 8. Factorials will be 0 factorial, 2 factorial, the next one will be what? 4 factorial, 4 factorial, this will be raised to the 4th. What do you think's happening with the signs? You're going to keep alternating. Alright? So I think you know how to deal with that. But before we do that, let's talk about this thing going by 2's. Anybody know a math formula that makes things go by this? Like 0, then 2, then 4, 6, then 8. Does anybody got a formula for that? 2. Put that in your notes. That's what we need. All we have to do is put a 2n on these powers. That's what makes things jump by evens. Try it. Plug a 1 in there. What do you get? 2. Plug a 2 in there. 2 times 2 is 4. Plug a 3 in there. 6. That's the math formula for making values go even. Hey, and while we're at it, we might as well include it right now. What makes things go for odd values? Like 1, 3, 5, 7, 9. Anybody know what that would be? It's similar.
2n plus 1.
Gosh, you're good. Would you put that in your notes? They know. 2n plus 1. Check it. And would you check this? Plug in a 0. What number do you get? 1. Check it. Plug in a 1 now. With 2 times 1 plus 1. 3. Plug in a 2. 5. So there you go. This does what? Evens. This will do odds. Hey, does anything else do odds? You could actually do 2n minus 1 if you wanted to, but then you'd have to shift this number right here. You did like a 2n minus 1 in there. Something before. Sometimes you can say, you can call it 2n minus 1, but then you gotta talk about where you're starting. That may affect where you're starting. All right, we're going to do the 2n thing. So, can you help me write this? Looks like we got a x minus pi over 2 raised to the n power? No, it's raised to the what? That's what we're saying. It's going to be to the 2n, right? You plug in a 0, you get the what? 0. What's the next number you plug in? 1, it jumps to a 2. 2 down. Hey, what if you saw this going 1, 3, 5, 7? I would have used what? The 2n plus 1. All right, what else? What's in the bottom? Help me out. Is this right? Excellent. What's wrong? That would go 0, then a 1 factorial, then a 2. It's jumping. Even factorials. So what do I put here? And how should I write this? I should put a... Should I put a parentheses around that 2n so we know that it's the 2 times n getting the factorial? You know, if I just wrote this, I'm worried you might think I'm just saying do the factorials and just keep multiplying 2's, right? I'm going to write it like that. Now, is there anything missing? Look carefully. Good. Good eye. What am I forgetting? The signs did what? Positive, negative. What makes things alternate? And I just put that funny little... Is it just -1?
To the n.
It's either -1 to the n, or we might have to use -1 to the n plus 1. You got to help me out with this. We actually got to study this.